Another type of non-parametric test is one that you can carry out on independent data which is not normally distributed, but where you want to compare the means, or in this case, because it's not normally distributed, the medians between two groups of data. So in this case, it's called the Wilcoxon or Mann-Whitney or U test. You don't need equal size samples of data, although it is a good idea to have them quite similar. You don't want to have collected 5 from one group and 50 from the other. So what you're going to do is you're going to put the data in order of magnitude from the smallest to the largest. You need at least 5 experimental units in each one of the samples, and it's an analogous test for parametric data. It's called the independent sample t-tests. So here's a set of data that comes from periwinkles on a beach in Porthcrawl, which is in Wales. So what you've done is collected periwinkles, which are small snails, small sea snails that you find within the sand on beaches, and you've collected them from 2 different regions of the beach, the lower shore and the mid shore. You've measured how long they are in terms of millimeters, and you want to compare, is there a difference in the size between the lower shore and the mid shore? This might suggest that there's tidal evolution and that there's different properties between the lower shore and the mid shore, that they're evolving into separate species or subspecies of periwinkles. It's going to be a bit of a grim experiment, probably done in December, where you send some poor postdoc out with a bucket and spade to the shore to find these things. And look at the size of them. They're small. This is going to be quite a challenging experiment. So what does SPSS do to do that comparison? What it first does is it puts all the data in order. So it finds the smallest out of the 2 groups, and that calls that number 1. The next smallest is number 2, and then it goes all the way through until it finds the largest, which will have the number n being the total number in both groups 1 and 2. So the largest one in this case is clearly 13.5. If you have 2 or more values that happen to be the same, then it's going to assign a midpoint for the ranks. So if the 5th and 6th thing have exactly the same number, then it will give 5.5 to both of them. You then figure out the ranks of the total sum of the ranks for every one of the data points in the first group, and the total sum of the ranks for all the data points in the second group. You count the observations for the first group, n1, count the observations for the second group, n2, and you look at the difference in the ranks between the 2 groups. Now, if these 2 things clearly came from 2 separate species which had different size profiles, what you'd find is all the smallest ones would be in group 1 and all the largest ones would be in group 2. So if you had 10 in each group, and all the numbers from 1 to 10 were in one and all the numbers from 11 to 20 were in the other, that would be obvious. And so the total sum of the ranks would be the sum of the numbers from 1 to 10, which happens to be 55, and the total sum for the ones from 11 to 20 is 155. So the difference in the ranks between the first and the second group would be 100. That's as perfect a separation as you can possibly get. So imagine it, another way of thinking about it is a pack of cards analogy. Imagine the black cards at the lower shore and the red cards at the mid shore. You have 13 cards of each. Shuffle the cards and placing them face up. How likely is it that you turn up 13 red cards come up first and then the 13 black cards in terms of order of them coming out of the pack? Instead of the order of them coming out of the pack, what you've done is arrange them in order of size. So if you get a mixture of sizes as you go from smallest to largest, if you get a mixture of groups, if some comes from mid shore and some from the lower shore as you go up, and there's not a preponderance of either the smaller ones or the larger ones being in the lower or the mid shore, then you won't see any kind of difference. What does the data look like? You've got 2 columns, one is shell height and one is location. This is exactly the same as you'll need to set up for parametric tests and t-tests. So you have a numerical number, your numerical variable, and you have a grouping variable. And this is an example of what we call long data. You don't have 2 columns of the shell heights at lower shore and mid shore. you have one column that says height, and you have one column that says midshore or lower shore, which are the 1 and 2 locations. So if you see, there's labels applied to them, but again I've changed them to numerical values to make it easier to type the data set. It also makes it smaller in terms of file size. So you've got those two groups. So how do you run it? So within SPSS, these are fairly easy, because what happens is you have a wizard which will take you through the process of running the test. So first thing you need to do is go to Analyze, Non-Parametric Tests, and these are independent samples. There's no connection between the shell height at the lower shore and the mid-shore. They're different periwinkles. They're not related. Once you click on that, you'll open up the wizard, which has 3 separate tabs: Objective, Fields, and Settings. So the first thing, you can do it fully automatically. Yeah, we want to do that. We know we want to compare medians, so we could actually click on the second button which says Compare Medians, or there's Custom Analysis. You don't want to do that unless you really know what you're doing. The next tab is Fields, which we need to go to, and in Fields you want to put in where is the variable you want to do the test about. Now we're doing a test about shell height, so that goes into the test fields, and you need a grouping variable, and in this case they're grouped by location, midshore or lower shore. Finally, the third tab is on Settings, which allows you to either automatically choose the test, sounds good to me, we want as much automatic as possible, or you could customize. So if you click on Customize, you can see grayed out there that it has Mann-Whitney U test for 2 samples. That's the test that we want it to do, so we could specify that, but it should automatically choose that anyway. Once you've done that within the 3 tabs, you can then press the Run button. So when you press the Run button, you will get this output. So the first thing you get is Hypothesis Test Summary. So it says the null hypothesis is the distribution of shell heights is the same in the 2 different locations, midshore and lower shore. It carried out an independent samples Mann-Whitney U test, and it found a p-value of 0.264. This is not below 0.05, so you can't reject the null hypothesis, so it's actually telling you you need to retain the null hypothesis. Now, as I said before, if you think about the process that it goes through, the total number of things in the sample is 26. The Mann-Whitney U statistic, the difference between the ranks of the 2 groups is 106.500. There's another variation that you can do, which counts the differences in the ranks compared to the perfect difference in a slightly different way, which is called Wilcoxon's W. For this particular piece of software, it uses the test statistic, which is the Mann-Whitney one. The difference between Mann-Whitney and Wilcoxon is nothing. It gives you exactly the same p-value, but you would just go to different tables of data to find out what that p-value is. As well as that, it gives some histograms showing you the spread of the data at the lower shore and the mid-shore, and here, unsurprisingly, the 2 histograms overlap with each other quite clearly, so there's no difference between the height of the shells in the lower shore and the mid-shore.